Welcome, Mindsetters. You have joined us on Spring School, and we are live. As John says, we are in for an absolutely shocking show. Hey, John.
That's absolutely right, Katlego. Guys, we're in for a shocking show because it's all about electricity. That's right. Today we're going to be dealing with a whole lot of stuff, Kat.
Okay.
We're going to do with static electricity, revision of grade 11 stuff, capacitors. Those can be really shocking. You mustn't touch a charged capacitor.
I'm not trying to
And
touch
then we're going to do some Ohm's law and some circuit problems, electrodynamics. So you can see, full show.
Oh, wow.
Lots of stuff to do. But guys, this is where we need your help. If you have a particular question, won't you please post it on the page?
Exactly it.
We want to know where you need some help.
Yeah.
And we'd be prepared to answer anything.
We are prepared to answer anything. As you know, John is the best science teacher here at Mindset. So you guys need to send in anything that you need to send because he is here for you. I know he wouldn't be here if it wasn't for them. Hey, John.
Absolutely. We're here to help you. And we really want to make sure that you do the very best you can at the end of this year.
Of course.
But we've got a competition question.
We do.
So
You can go over
it?
to the board. Let me tell them about how to get hold of us first, and then I will pass it over to you. You guys know today is absolutely dynamic because it is part of Spring School, and there are various ways to get hold of us. You know already our Facebook page, facebook.com/LearnExtra. Our Twitter handle is @LearnExtra, and our pep text as well. Guys, you can pep text us, and our group code is LearnExtra. Also, you can email us at win@LearnExtra. Another way you can get hold of us these days is that you can actually SMS us on 083 448 8810. That is 083 448 8810. Remember to add your name, guys, to the emails, the pep text, and the SMSs so we know exactly who we are getting hold of. Also, before the competition question, wait, we have prizes for you. We have 3 CDs. We have the Soul Candy, we have the Mikasa Soul Candy, and we have the CD by Universal, that's Top Mafia. If you're a winner, you get to win all 3 of these, as well as the Physical Science Notebook, guys. These are study notes for grade 12. So you need this, you know you need this, as well as a t-shirt. I have a t-shirt right here, and it's like the one that I'm wearing. I know that you guys love it, so make sure that you are the winner for today. We are ready for you to read out that question, John.
Thanks, Katlego. It's great to be with you. Now, have a look at the competition question. Not too difficult. As you know, it's about electricity. So here we go. It tells us the following. It says a voltmeter is connected across a battery. Now, there's an interesting idea. It's connected across a battery that's in parallel. So the voltmeter is in parallel to the battery, and it reads 12 volts when a switch in the circuit is open. But it reads 11,5 volts when the switch is closed. That's interesting. Important information to take note of. Right, what else does it say? It says an ammeter is connected in series to the battery, and it reads 0 amps when the switch is open, and it reads 1 amp when the switch is closed. Here's the part of the question. What is the internal resistance of the battery measured in ohms? And you've got these 3 options. A, 0 ohms, B, 0,5 ohms, and C, 1,04 ohms. The code that you must put in is 4331. Right, guys? Hope you've got that. Get your entries in. We're going to keep the competition open as long as we can, but somewhere just after 12 o'clock, about 10 past 12 or so, we'll let you know that we're closing the competition. But you can enter on any of those platforms, email, SMS, pep text, or on Facebook. And we've created 2 places for you to enter the competition on Facebook, either on the main page or on the events page, which is the Spring Day 3. But please, guys, enter your answers as a comment to the question. If you put it anywhere else, we'll get it lost. We won't be able to put your name into the competition. So please put it as a comment to the posting of the question. Guys, I hope that's right. Have I missed anything,
No,
Kandego?
you haven't. Actually, maybe you have. There is this important thing right here. This is the Spring School booklet, guys. This you can download on Facebook as well as order it. This is very important because it has some questions and the answers and everything that you need, guys. So make sure this is going to be your tool for the rest of the year because it is so important. You can download it on any subject, but today, download the physical science one because it is going to be an awesome show. Another thing, thank you to Liberty for bringing us such a fantastic show.
Great.
Take it away, John.
Katlego, that's great. Now, guys, the Spring School Notes, they give you lots of tips and revision ideas, and it will go through the questions of the sessions that have been broadcast since 9 o'clock this morning. Those same sessions are going to be broadcast a little later, in fact, tomorrow morning as well, early hours. If you'd like to do some revision late at night, early in the morning, then make sure you've either PVR'd it or recorded it or stay up and do some studying. Guys, October holidays, time for revision, time to make sure you've got everything sorted out, but also treat yourself. Have a break every now and again. So that's why we're broadcasting both in the morning and late at night. And of course, we'll give you information about when you can get repeats of even this live show. Right, what we're going to do today in this show is we're going to be taking a look at some questions from the supplementary paper that was written at the beginning of this year. But of course, we can take your questions as well. So get those questions in. I'm going to start working through the February-March 2012 paper. We're going to start with the multiple choice questions and just extracting those that are relevant for electricity. So let's have a look at the first one. First one that we're going to look at tells us that we are dealing with electrostatics, and it tells us the following. It says two identical small metal spheres are insulated, are placed on insulated stands, and they carry equal charges. They're placed a distance d apart. Each sphere experiences an electrostatic force of magnitude F. So when you get a question like this, make sure you pick out the main information. And what's really important, I think, even if they haven't given it to you, is on the side, on the question paper, you could even draw a little sketch. So I like to draw little sketches to be able to illustrate what's happening. So I would do something like that, and I would say they're placed a distance d apart. So let me change the color of my pen so you can see that. And we recognize that they have equal charges, so I'm going to call it Q1, and I'm going to call that one Q1 as well, so I don't forget that they're equal. Having got that, now what does it say to me? It says the following. It says the spheres are now placed a different distance apart. Notice that the distance has changed. It is now half d. What's going to happen? So here's the scenario. We've got Q over there, or this particular little diagram, which has been drawn as one. We're now going to draw them closer together. We're going to no longer have them d apart. We're going to draw them a little closer together. The distance has changed. It is now half of d. So there, that's the diagram. Notice that Q hasn't changed. They haven't touched. That's still Q1, that's still Q1, same magnitude. We haven't changed the charge. We've changed the distance. What should you be thinking whenever you get an electrostatics question like this? You should be thinking Coulomb's law. Before you even look at the possible answers, you should be revising for yourself that F is directly proportional to Q1 over Q2, and it's inversely proportional to R squared. The other way of saying that is we can say we know that for this example, we're not going to worry about the charges. So we're actually going to just look at the relationship between the force and the distance. And we know that force is directly proportional to 1 over r squared. What does that mean? Well, guys, you really need to know this. If we change the distance, it changes the force by a factor of 1 over r squared. So how are we going to work this out? Well, I like to do some substitution. So I'm going to say to you, let's do the calculation, and then we'll look at the possible answers. So I'm going to say, let's say that the old force is F. And we're going to say this is the old one. And we're going to call it F. And we're going to say, let's say that it is equal to a constant. And then it is equal to, and it's not the normal constant. It's just a big K, a particular constant, because the distance and the charges aren't changing, and we know we've got the charge in any case, 1 over d. And I'm going to put 1 over d squared there. Now, what is the new charge? The new charge is going to be equal to K, the same K, which includes the 9 times 10 to the 9, as well as the charges, times, now I'm going to put over here 1, and in brackets, 1 over, in brackets, half d squared. And it's all squared. So half of d in brackets, all squared. Now, if I do that squaring process, look what I get. I get a K times, this is the new force, 1 over, and if I square a half, I'm going to get a quarter. Half times a half is equal to a quarter. Okay, so I keep that, and I'm going to get d squared. But I can simplify that a little bit further. Can you see that when you divide by a quarter as a denominator, what happens? If you're dividing by a fraction, you're told you must tip in times. So we're going to invert that, and we're going to get is equal to K times, I'm going to take that value there of a quarter, and I'm going to invert and multiply. So I'm going to say it's 4 over 1 times, and let's go back to my original, 1 over d squared. Now, guys, compare what I've got over here, compare this value to my old charge. It was K times 1 over d. I hope you can see that we can rearrange this, and we can take out the 4 over 1, which is just 4, and we can then write it as equal to 4 times K 1 over d squared. And if we look at that, we say, well, that's just 4 times F old. Okay, so what's happened? We've halved the distance, half, 1 over 2, and we've increased the force, the magnitude of the force, by 4 times. Because if you square 2, you get 4, and the 1 over makes it 4 times. So it's half, inverted, becomes 2 over 1, square it, becomes 4. Hope you can see that relationship. Make sure you know it for what happens when the distance is halved, the distance is quartered. What would happen if the distance is quartered? Well, a quarter times a quarter is a 16th, so the force would increase by 16 times. Get to know those values. Even if you decrease the distance by a third, made it 3 times smaller, well, what's going to happen to the force? 9 times. Get those ratios correctly in your head so you've got it all sorted out. Now let's go and answer the question. Have a look. You see I did the calculation, and now all I've got to do is I've got to compare. When we're dealing with multiple choice questions like this, what we do is we work out first of all, and then we compare. And we say, well, clearly the answer must be the one that we've got, which is 4 times F. Read the question again. Make sure that we've got it correct. The magnitude of the electrostatic force, the new electrostatic force, each sphere experiences is 4 times the force that it originally was. Guys, I hope that makes sense. Please remember that this type of manipulation, where you're not given numbers, you need to know really well. The 1 over r squared rule is important for Coulomb's law. But you can also get similar sort of relationships when you deal with electric field strengths, when you get dealing with capacitors. You need to be able to manipulate. We're going to do one more of these, but I think we need to go for a break because we're running out of time for this first segment.
Let's go for a break then. Guys, Remember, during this break, the competition question will be up again. So then you'll have another chance to quickly just jot it down for yourself and send us through anything that you need to send us through. The answer, questions on what John has done, anything that you wish. See you right after the short break. Welcome back, Mindsetters. If you have just joined us, we are doing physical science, and today we are focusing on electricity. It has been an awesome show so far, so if your friends perhaps haven't joined us yet, let them know that, you know, we're the home of the brainers. They must come join us. Also, I need to remind you to answer the question on the events wall or comment under the question itself. Don't just say it like randomly, because then we might lose all your answers. Also, you can SMS us, pep text, and email us. So don't forget, guys, there are so many platforms for you guys to use. If your Facebook perhaps isn't logging on, send us a quick SMS. Or if anything else, if you don't have email, then jump onto Facebook. You know what I mean? So there's many places that you guys can answer the question. And another thing, keep asking us anything that you need to ask us, Matrix. There are so many things you guys need to know. Flip through all your notes and make a note where you guys have maybe gone wrong on your prelims or something that's confusing you, because that's what we're here for. We're here to answer all your questions. Over to you, John.
Thanks, Katlego. Now, guys, remember the reason that we're dedicating this time to do electricity is because many of your teachers may not have had time to revise grade 11 electricity with you. So that's why we're doing electrostatics and we're doing some circuit problems. We will get on to some electrodynamics as well. But anything of that section, any of those questions, we'd love to hear from you, we'd love to take. It's a really important section. You know what? It counts between 40 and 50 marks out of 150. So guys, you better make sure that you've got this. You know what? If you do enough practice, you will ace the section. There's no reason why you can't get 100% for the section, because it's so interactive and there are so many great ways of solving a problem. You'll see later on, we'll be able to check our answers as well, particularly in circuits. If you're very familiar with circuits, you'll be able to know that you've got the circuit problem right. But let's go into one more multiple choice question, which was dealing with relationships. Here we've got a second one that deals with relationships, and it's related to a circuit problem. So have a look at it and let's see exactly what it says. It says in the circuit diagram below, the internal resistance, very important, of the battery and the resistance of the conducting wires are negligible. Guys, that means that the resistance of the wires is 0 ohms and the internal resistance is 0 ohms. So we need to recognize the word negligible, bit outdated, means ignore it. It doesn't matter. We sometimes in our physics papers say that air resistance is negligible, friction is negligible. There's a little bit there, but we can, for the purposes of our calculations, ignore it. We know that it exists, but for this calculation we're going to put it to 0. The EMF of the battery is E. So here again, they've given us a nice circuit, and they've told us that the EMF, what is EMF? It's the maximum potential difference that the battery can supply. It's also the potential difference that your voltmeter, if it's connected across your battery, will read when the switch is open. So when the circuit, there's no work being done in the external circuit, when the switch is open, that potential difference across a battery connected in parallel will be 0. Something about that in the competition question I think you'll remember. So that's what EMF is. Now, what does it say? Let's have a look at the circuit first of all. We recognize that we've got 3 cells connected in series, one after each other. We go from the positive terminal to the negative terminal, direction of conventional current, from positive to negative. So that's the conventional current. And we recognize that it's going to go through the ammeter. So the ammeter here is going to be in series to the battery. And so it's going to read the maximum current. of this circuit. We then recognize that we get to this point. Now let's see what happens at this point. We've got a switch for this bottom part of the segment, which is open. So actually that's just, we're going to ignore that. We're not even going to worry about it. We're going to ignore it totally. It's just there to confuse you. So what happens next is all the current is going to go in this direction, and it's going to go through this resistor. So this resistor is connected in series. It's in the main circuit, and it's connected. It has a resistance of R, and notice, it's connected to this resistor. There's no other branching, so these two resistors are in series as well. The same current goes through them. That's how you can tell they're in series. Now, what about the voltmeter? The voltmeter is always connected in parallel. That's the way a voltmeter is designed. It's a high resistance instrument so that the majority of the current goes through the resistor that it's measuring, because it's measuring potential difference. It's taking a dipstick measurement before the resistor, and it's taking a dipstick measurement after the resistor, and it's comparing the difference between those two in terms of the energy that the charges are carrying, or the amount of work done per unit charge that is going through that resistor. So we recognize that the current is going through this resistor, R, and it's in series with R2, and this voltmeter is reading just the potential difference across R, the first resistor, across R. Okay. Now, looking at it, let's read the rest of the question. It says, when the switch is closed, okay, very important. We need to recognize something here now. It's not just asking about when the switch is open, it's asking about when the switch is closed. I said initially we can ignore that. Well, here we go. We're going to not ignore that now. We're going to actually erase my readings over there and say, what's happening when the switch is closed? When the switch was open, it was just a simple resistor plus resistor in a series circuit. What's going to happen when the switch is closed, guys, is now the current needs to split up. But here's the thing. Which way is the current going to go? Here's a choice for you, Katlego. If you have to go on a road and you have to pay 1,000 rand to go from point A to B. Okay? And there's another road that you pay 0 rand to go from point A to B. Which one are you going to do?
The 0 rand one, definitely.
Okay, and that's exactly the way that current looks at it. Guys, current always chooses the path of least resistance. I think that's sometimes what grade 12 learners do. They try and take shortcuts.
Yes.
Guys, don't do that. You need to do some work every now and again. But here, this current tells us they've got a choice. If this switch was closed, now look what happens when the switch is closed. What is the resistance of this part of the circuit? Well, hopefully you can see along here, no resistance. Okay, there's no resistor there. Where are you going to go? Are you going to go through the resistor and pay the energy to get through that resistor? Or are you just going to say, no, I'll be chilled. I'll go through where there's no resistance. Like I said to Katlego just now, are you going to pay the 1,000 rand or go the route from A to B and pay nothing? I think what we know is that we'd all pay nothing, and that's exactly what the current does here. So all the current passes through the bottom part of the circuit. It then goes through the 2R resistor, and nothing goes through the current. No current goes through here. Absolutely nothing. You've got a choice between paying money or paying nothing. You're going to pay nothing. So we need to bear that in mind. So go back to the question. The reading on the voltmeter V in volts. Okay, so what do you think it's going to be? Remember what the potential difference is? Potential difference is going to be I times R. Now guys, if I current is 0, what's the reading on the voltmeter going to be? Think you got it? Sure? Because remember, if the current is 0, 0, doesn't matter what size that resistor is, the potential difference is going to be 0 volts. So that's what this potential difference, the voltmeter reading is going to be. The answer that we're looking at is A. Please make sure you know how to explain it. Okay, I want to show you though. Let's just change that question for a minute. Because some of the other answers could be relevant if we kept the switch open. So let's say we're going to keep the switch open and we're going to go as normal. So we're not going to do what the question says now. We say let's keep the switch open. What is the answer going to be? What's the reading on the voltmeter going to be in terms of this? So make it very clear to you, we're not doing this question. We're saying, how about if the switch was open? Switch is open, open switch. What are we going to find? Now, guys, if it's an open switch, then what you need to recognize is that we've got this resistor in series and this resistor in series. Now, so we've got two resistors in series. We've got resistor and resistor in series. This one is 2R and this one is R. We know that the total potential difference across both resistors is E. Okay? That's the reading across the battery. So what is the one across R going to read? That's where the voltmeter is. And this, we don't have a voltmeter, but we do have a potential difference across it. What do you think the potential difference across here is going to be? If we put a voltmeter, what would we expect to find? Well, here's the interesting thing. You need to remember that resistors in series are what we call potential dividers. So the total potential difference is divided in the same ratio as the resistance. So have a look here. We have one part of resistance there and two parts of resistance there. So the total number of parts of resistance is 3. So what we're going to have here is 1 out of 3 E over there and 2 out of 3 E over there. Where did we get the E from? Remember, E was the EMF, and it's the total which was measured across the battery. Guys, this is only for open switch for that particular circuit. The important thing that I wanted to get to you and to make sure you've got very clear is the ratio idea. Potential difference in a series circuit is going to divide in direct proportion. So if the resistance is 1:2, the ratio of the potential difference is also 1:2. So there'll be one part of potential difference over here, two parts of potential. So when you've got a ratio, remember the total number of parts, 1 to 2, 3. So 1 out of 3 of E, 2 out of 3 of E. Guys, just to make another point here, because it's really important, that if we're talking about potential difference, that if these resistors were in parallel, so instead of them being in series, let's say that we have these resistors now in parallel rather than in series. So this one is 2R, this one is 1R, and they are in series. What I want to know, and I'm going to ask you to post this on the page, we put a voltmeter over here, and we put a voltmeter over here. We call this one V2, and we call that one V1. What are the readings on V1 and V2 in terms of the fact that we've said overall that there is a EMF across the battery of E? Okay, so in terms of E, what would V1 and V2 read? Guys, please post it on the page. We're going to make sure that we collect as many of those answers, and we'll get back to this a little later. I hope that you can see that by doing a past paper question, it's not just about doing the question. You have to start thinking and applying your knowledge and saying, Where can I learn? What's this examiner talking about? If he's asked the question about the ratio of things in series, what if he asked the question about the ratio in parallel? Similarly, he could say to you, this year, this paper, he asked about the ratio of potential difference. What happens if he asked about the ratio of current in parallel? Well, there's an interesting question for you to think about. We'll come back to that. But Katlego, you know what?
Let's take a break, eh?
I think we've almost exhausted this question.
Okay.
But before we go to the next one, let's take a break.
Let's take a break, guys. During this break, you can get refreshed and stuff, but don't forget that the challenge question is up during the break. So in case you missed it, this is your chance to get a hold of it and jot it down. It's also on Facebook, so don't forget to check that out too. See you just now. Welcome back, Mindsetters. If you have just joined us just now, right now, we are doing physical science. So make sure that you get up to date on the page. All the information is on our Facebook page, guys. We never leave you stranded. If you pop onto the page, you'll see that I've also just given you the link for the spring school booklets, because I know many of you are asking, where can I get this booklet from? The link is there. There's also a link to all our schedules. There's a link. I'm also telling you now that there's a repeat at 4:30 today. I know that some of you are like, oh, I'm going to spring school at school or summer school. I don't know what you guys call it these days. But you're going to school, you can catch it later at 4:30, as John said, or later during the early morning. So if you want to wake up at about 4 in the morning, you can actually do that. But remember that rest is very important, guys. So get your rest and get your study on. Once you have a good balance, then you will pass so well. And remember to send us those results, because we are looking forward to you guys passing, because that is what we're here for.
Absolutely. Katlego, thank you so much. Guys, we've been doing some multiple choice questions from the February-March 2012 paper. I've been trying to show you that as you go through a paper, it's about revising the content as well. Make sure you can work things out. Multiple choice is not for guessing. Having said that, when you get into the exam, make sure that you answer every multiple choice question. So even if you're not sure, guys, don't leave a multiple choice question blank ever. Okay? If you don't get the right answer, I'll give you permission to guess. First of all, do some calculation though. Right, we're moving on to some longer questions. I'm going to start by doing a typical Coulomb's law electric fields question. This one is really quite challenging and quite nice. So it's a little different to what you might have seen before, and it's got some theory in it. Just helps us to do a checklist, a tick box to say, yeah, we know that, we've got that all sorted out. So let's have a look at it. It's taken from the February-March paper, and it was originally question 8. What we're told here is we've got, look at the diagram, we've got two spheres, metal spheres, P and Q. They're on insulated stands, and we recognize they have a charge of plus 5 times 10 to the minus 9 coulombs. This one is also plus 5 times 10 to the minus 9 coulombs, so they're the same. They are both positive, and they're the same magnitude. They're placed with their centers 20 millimeters apart. Now, here's the thing that you need to know. As you're reading through an electrostatics question, please make sure that you've revised conversion of units. Because this time they gave you coulombs, which is the SI unit, but next time they might give you microcoulombs, or nanocoulombs, or picocoulombs. You need to know how to convert. And when you see millimeters, you need to convert millimeters straight away to meters. The easy way is just to say milli is times 10 to the minus 3. So 20 millimeters is 20 times 10 to the minus 3. Put it down on the diagram, and that's the distance apart. We also told that there is a point, a distance of 10 millimeters. So immediately I'm going to rewrite that as 10 times 10 to the minus 3 meters. Away from sphere Q, as shown. Now, the first part of the question was define electric field. Now, this is the theory question. It's based on your understanding of what an electric field is. Remember, an electric field is simply the region of space around a charged object where if you bring another charged object into that space, it will experience a force. So it's a region in space around a charged object where something with an electric property, electrostatic property, a charged object will experience a force. So you make sure that you've got that sorted out, and we'll move on to the next question, which is also kind of theory. It says, sketch the net electric field pattern for the two charges. Right, so remember, field line diagrams, we're going to draw those two charges. We've got P and Q, and I'm going to change the color of my pen and recognize that they were both positively charged. So what we need to do is we need to draw in the field line pattern so for two positive charges where they're going to repel. We recognize the field line is going to go outwards from a positive charge, so we can spread them out, radially out like that, but it's on this side that they're going to start to curve. They mustn't ever intersect, and they're going, oh, I've made a boo-boo, so let's just change that. They're not going to go towards each other. We recognize they're going to go radially out, and they're not going to be because they're opposite charges. We're going to recognize that there's something different happening here. So let's just redraw that. Make sure that you've got it right. Check yourself all the way. It's easy to make a mistake. So, where are we? We've got this one over here. Recognize now, positive and positive are going to repel each other. So we can't have them joining up. They're going to push each other away. Remember what the field line is actually showing. It's showing the direction of the force that a small positive charge will experience when placed in a particular position. So if I have to place a small charge, positive charge, in that position, what's it going to do? It's going to be pushed away. So what we find is we get this sort of thing happening. We find that it bends like that. And on this side, we're going to get it bending downwards. Similar pattern on this side. And directly in the middle, if we put a positive charge there, it's going to be pushed away from P and pushed away from Q, and so it's going to be stuck. There's going to experience a point where there is no net force on the object because the charges were identical. And so that's why this middle point, there are no field lines at that position. That's why we leave it blank. Recognize that a positive charge at this point is going to be experiencing repulsion from both P and Q, and that's why it's being pushed up. Okay, you need to know that diagram. Make sure you know the other one as well, where the one is positive and the one is negative. Make sure you also know the pattern for plates and for single charges, both positive and negative. So that was that diagram. Now, it's time to do some calculation, I think. So let's go to the next question and pull it up. It says, calculate the net electric field field at point X due to the presence of P and Q. Now guys, here we have a real issue. We need to do some calculation of electric field strength. And we know that there are two formulas. E is equal to F divided by Q, and E is equal to Q over R squared. Now, in this question, we aren't told a charge that is placed at a position in a field. So immediately, we've got the two formula. We need to decide which formula we're going to use. This one we can't use. We haven't been given a force, and we haven't been given a test charge. We've been given a distance. And we are given the distance of the electric field experienced at a position. So we're going to have to use this formula for P, and we're going to have to do it for Q. So here we go, and we recognize that it is P and Q, where the charge that we're looking at is going to be, in this case, P, and the charge over here is going to be Q. So we're going to have to do it twice. that looks like quite a lot of work. So I like to try and think about ways of cutting down the amount of calculation we're going to do. So let's just go back to the question and see if we can find something that will help us and will help us choose exactly what we're going to do. So have a look. What we're saying is that P has an influence at position X. That is 30 times 10 to the negative 3 meters away. We also recognize that Q has an influence at that point. We're going to have to calculate both those electric field strengths. Notice, though, that this one is half the distance away. So when we take a look at 10 and we take a look at, it's not half the distance, it's it's a third of the distance. So if we compare the distances, please notice that this one's 10 millimeters, whereas from X, P is 3 times the distance. I hope you can see that there's a factor there that we can use. So I'm going to start by working out the stronger electric field, the one that is closer. In other words, I'm going to work out the electric field that is produced by Q. So let's do that. Let's substitute in, and then we'll be able to add in the next one. So let's go for it. We're going to say Q, and we know that that was K. That was, remember, it was a K there as well. I missed out the K. KQ of the charge, R squared. Now let's substitute in, and you remember that the K is 9 times 10 to the 9, and that's on the data sheet. We can pick that up. The magnitude of the charge back in the question was 5 times 10 to the negative 9. So they've been quite kind to us by getting the values at least to cancel out on the exponents. And we recognize that the distance here from Q was 10 millimeters, which is 10 times 10 to the minus 3 meters, and we need to square that. So if we put that all into a calculator, let's get the old calculator up, move it across, and let's see if we can get the readings in. 9 exponent 9, and we want to multiply that by 5 exponent minus 9. We're going to divide it all by the factor of 10 exponent minus 3, and we get an answer of 4,500, and here we're going to use the units, the correct units of Newton per Coulomb. 4,500 Newton per Coulomb. So 4,500 Newton per Coulomb. Okay, and in which direction is that electric field? Notice we had a net charge, calculate the net charge at point X due to the field. In which direction is the electric field? Well, we should recognize from our previous diagram back here that X was over here somewhere, so it's going to be away from that point. So recognize, we must give the answer that it is away. Now, that's quite a big electrostatic field. What can we expect if we do it for the second one? Well, we can do it like this. We can do the calculation, but I like to take some shortcuts. And as I said to you, what I recognize is that the distance here is going to be 3 times more. So I'm going to work out the electric field based on the fact that the charge has changed. So I know that the electric field for E, what we recognize is here that the distance R has increased by 3 times. So if I say EQ, was the old charge, and that was equal to 4,500 newtons per coulomb. I want to be able to work out P. If I've increased the distance, recognize again that I've increased the distance by 3 times. Remember, we've got E is directly proportional to 1 over R squared. If I've made that 3 times bigger, what am I going to do to the 3 squared? It's going to make this a 9th. Can you see that? So if we square 3, we're going to get 9R squared over 1. So if the first one, EQ, was equal to a certain value, then we recognize that, and we've got that value down, that this one is going to be 1/9. Sorry, let's just do that it's different. This is EP. And say to ourselves, it's going to be different. EP is 1/9 of EQ. Why? Because it is 3 times further away. So the factor of 3 squared and inverted is 1/9. So does that make sense? I hope it does. And you can see now that it is a shortcut for us to say, well, we know that EP is now going to be 1/9 times 4,500. And I think that's a whole lot easier than, so if you know your maths and you know how to do this, we can just simply times the answer by the fraction of 1 over 9, and we get an answer of only 500. So please notice, probably even have done that in your head, 500 Newton per coulomb, and these are vector quantities. Notice this is also a way. Go back to the original question and notice it said net electric field. So we've got to make sure we add those two together, and we're going to say our final bit, our final answer, recognize we've got the net electric field is going to be both of those. It's going to be EP plus EQ, and because they are both away, they're both positive, so it's 4,500. I've probably got them around the wrong way, so let's just make sure that that's the right way around. It's 500 plus 500, the one that's further, plus 4,500, which I think you can do in your head, 5,000 Newton per coulomb. And don't forget, away from at X, from P or Q. Okay, so at X, guys, because they're both pushing the charge away, a positive charge, we'll be experiencing an electric field away from them. Hope you can see how we've done those two calculations. Katlego, back to you.
Thank you, John. Guys, we're going to go for a quick break. Wow, you guys are really on the ball. Don't worry, just go for a quick break and we'll be right here when you get back because there's a lot more to get through. See you just now. Welcome back, guys. Physical science has been so much fun this morning, and now it's still morning, luckily. Don't forget that the competition will be closing in a few minutes. So if some of you are delaying in sending in those answers, please send them through right now, guys, because it's very important that we get all your answers so that when it closes, we can actually just draw your name out of a hat easily. If you have answered on randomly on the page, it may not be considered. So make sure that you have gone back to the events page, pep text, SMS, email, so that we can get all your answers in before it closes. Remember that there's some awesome prizes to give away today. So make sure that you are the winner. So maybe even post an answer many times just so that we get that you are here. And if you have any questions, this is also the right time to send them through because John will be going through some of your stuff. And some of you have been asking stuff on what John has done so that you know that all your questions are covered and we are with you 100% today. Over to you, John.
Guys, thank you so much. Thanks, Katlego. Now, you know what? I did something that I know a lot of learners make a silly mistake with. And so, you see, anyone can do it. We need a check. Now, I say it to my learners every year. When you've got something that's got a square in it, make sure you check your squared. You know what happened this morning? I didn't square. So just go back to that calculation very quickly. You see, we wrote it down over here. We wrote it down correctly and said we must square the value here. We must square this value. And when we put it on the calculator, I forgot to square it. I forgot to put the square in. So the correct answer shouldn't be just 4,500, but it's got a couple of extra zeros on it. So you can see when you square it, you get a couple of extra zeros. And so we make sure that we've got the answer. There it is. It's 450,000. So if I am to correct that, let's just make sure we've got the correction, and we're going to do that and just close that down.
At least we know all our mindsetters are awake.
They're awake for sure.
They're so awake.
They're so awake in the morning. So the correct answer is just a matter of changing the value. But guys, that's the thing that you should be doing when you get your paper at the end and you've finished all your answers. Make sure, there's one thing you must make sure of when you're checking your exam paper. Make sure that every vector, every answer has a unit, and every vector question has a direction. And if you see a square in it, make sure you've either squared or square rooted. Very important. So what we reckon that the correct answer is 450,000, because Newton per Coulomb. Now, it will obviously also affect this one, because this one was going to be 450,000. It will work through, but the fact that it's 1/9 means that we recognize that we've got it right. Now, I know that some of you have been asking for circuit questions, so I'm going to skip back originally to the question that I posed to you earlier, and then we're going to go to a circuit question. Remember this question. I recognize that some of you, like Justin and a couple of others, have answered this question. You've got it right. Make sure that you remember that potential difference in parallel, across resistors in parallel, is going to be the same. So the value of V1 would be E, and V2 would also be E. So make sure that you understand. When resistors are in series, they're potential dividers. When they're in parallel, potential is the same, but they're current dividers. Let's just make a note of that and recognize something. That if we were to say, what happens to the current that goes through here? Remember that current divides in inverse proportion. So the current, more current, goes through here. So what we would say is 2I goes through there, and 1I, one part of current, goes through that one. So it's inverse proportion. Make sure you've got your proportionalities all sorted out. Right, let's move on to our circuit question, because I know that there's been some people that have been saying, let's do a circuit question. So here we go from the February-March paper. It tells us in the circuit diagram below, the battery has an EMF of 12 volts and an internal resistance of 0.8 ohms. The resistance of the ammeter and the connecting wires may be ignored. So have a look at the circuit diagram now, and we see 12 volts, 0.8. What have we got? Analyze your circuit. And the way that I like to analyze it is to use my pen to say which parts are in series, which parts are in parallel. This is something that you do even before reading the rest of the question. So I take my pen along and I say, right, okay, this part must be in series. So I put an S over there. We recognize that that's where the current is going to be maximum. We recognize as well that the current divides, so use a different color over here, and see that that's one part of the loop. And I'm doing this for current, and that's another part of the loop. And recognize as well that these two parts, that's in series with that. So I've got two resistors, even though they don't look one after the other, at the second branch, they're in series. So we recognize the yellow and green are in parallel. We've got branch 1 which I'm just going to call it branch 1, and in yellow we've got branch 2. And they're in parallel. Now, notice when we come back together here, this is where the current is maximum, and it's maximum all the way through. So the reading on the current will be the same everywhere it's blue, but here it's going to divide. The current is going to be less over here. It's going to be less over here. It's going to be a different current over here. But the potential difference, that's another story. So what does it ask us to do? It says calculate the effective resistance of the circuit. Now, guys, when they say effective resistance, they're meaning the total resistance. That includes the internal resistance, and we need to make sure that we've got that very clearly sorted out. So the effective resistance of the circuit, are there different ways of doing it? Well, yes, there are. What we are given, we are only given the EMF, and we are given the resistance. We don't know yet what the current is. And we don't know what the external potential difference is. So I think what we're stuck with is we're going to need to calculate each part of the circuit. So when you're given a question like this, we've analyzed the circuit, let's reduce the different parts. We're going to start with the parallel part. We're going to work out the resistance, first of all the parts added together. And so we're starting with the parallel branches. We're going to say we know that the resistance in parallel is equal to the resistance of branch 1, B1, plus 1 over the resistance of B2. Got that? Written that down. Now let's see if we can work it out. The green part we said was B1, and the yellow part was B2. We know that the yellow part is 4 ohms, but the green part, notice here, we've got an 8 ohm resistor and another 8 ohm resistor, and they're in series with each other. So in B1, the resistance of B1 is going to be R1 plus R2, which is going to be 8 ohms plus another 8 ohms, which is going to give us 16 ohms. So I have to work that out first, and before I can do the substitution to this. So I should really have done it on the side here, and simply shown you that for B1 we've got R1 plus R2, and I'm not going to rewrite it again, but simply to write the answer, which is 16 ohms, 8 plus 8, show you're working very clearly. So what is the potential difference? It's 1 over 16 plus, I'm sorry, not potential difference, resistance. 1 over that other resistor was 4 ohms. And now we've got a fraction. Katlego, I don't know about you, but lots of people, when they see fractions, they panic.
They run away.
They run away. Now, you can do fractions the long way. You can do it by trying to find out the lowest common denominator and all that. But guys, why panic? Why battle? You've got a calculator that deals with fractions beautifully. So let's go and see how to do this on the calculator. Pick the fraction button, and we simply have to fill in the 1 over 16, and then go out, plus fraction again, and we go up to the top, and we say 1 over 4, and we don't even have to think about it. It gives it to us, 5/16. Okay, so we've got it very clearly. We understand that we've got the correct answer of 5/16. But remember, that's not the final answer. So please don't think that's the final answer. And I've locked the board again. So that was 5/16. But that was 1 over R parallel. So guys, when we get that answer, 5/16, we recognize, therefore, R parallel is going to be 16 over 5. We must invert it and then write it down as a decimal to correct to 2 decimal places. And the fraction button that we can use is simply the 1 over x button, and give an answer of that, and that's 3,2 ohms. So 3,2 ohms is my answer there. If I select 3,2, put in the unit 3,2 ohms. Right, so I've now calculated this bottom part of the circuit, I know that's 3,2 ohms. What about that part? That's in series, and I've also got that internal resistance. So I'm going to say, guys, the total effective resistance now is going to be R effective is going to be R external plus little r, which gives me, let's do it, R parallel plus R1, or R in series, plus the little r, substitute in 3,2, plus the one that was in series, and I think you could see that was 2 ohms over there, 2 ohms, plus the 0,8, which was in the question. And it doesn't take much to see that's going to be 6 ohms. That's my total effective resistance of this circuit. Okay, next part of the question. And we move on, and it now says to us, calculate the reading on the ammeter. Now, look back at your question, and you'll see that the ammeter is reading the total maximum current because it's in series with the battery. So we need to get the maximum. And so what we're going to say is I is equal to V over R. And what we want here is a V max and R max, or R effective. So we're going to use the value that we've got. We know the V max is the EMF, which is 12 volts. We know that the total maximum or effective resistance, which we calculated just a few seconds ago, was 6 ohms. So we take that answer and we put it in over here, 6 ohms, and we get a current of 2 amperes. Okay, got it. Hope you can see that it's just about applying Ohm's law and making sure that you've got things very clearly sorted out. And so there we go. What about the next part of the question? It says, now we want you to find the reading on the voltmeter. Now, guys, there are different ways of doing this. And like always, there are multiple options. We know the initial current was 2 amps, and we know that this part of the branch was 16 ohms. 16 ohms, that's right. That part was 4 ohms. We also know that that's the information we've been given. 12 volts, 2 amps, 2 ohms at least, and 2 amps is the current. So where are we going to find the potential difference? Now, if you look at the question and you're stuck, you don't know where to go, what do? You've got to ask yourself what you really know. And what you know is that there are different parts of the circuit that have potential difference in them. So there are multiple ways of doing this. Don't just get stuck on one way. I'm going to leave you to think about it. Have a look at that question, and we're wanting to find potential difference across the 8 ohm resistor. You think you can do it? Well, why don't you see if you can post the answer on Facebook before I do it? We're going to go to a short break, though.
Okay.
And we'll pick it up directly after the break.
Okay, cool. And I'm going to do you guys a very big favor by putting the question up on the page for you. So answer it right underneath the post so that we can see who's on the ball today. See you right after this short break. Welcome back, Mindsetters. I've just read such a funny post. Vuelo says, these short breaks are disturbing us. There are too many. I agree with you. We should just go right through 1.5 hours just so that you guys can get everything that you need to get. But unfortunately, some people would complain because they do need their bit of rest or just a glass of water or their pen has run out. So that's why we have short breaks, just so that you guys don't have to worry about missing any part of the show just in case you need stuff. Okay, so the competition has closed now. So now you guys can focus on asking us questions. I'm looking forward to any questions that you may need to ask because that is what we're here for. Over to you, John.
Thanks, Katlego. Guys, I don't know that I could carry on speaking for an hour and a half. I certainly need to have a sip of water every now and again. Also, just refresh the page, check what's happening on Facebook. That's really why we're having breaks as well. Okay, now I hope that you've had a chance in that break to engage with this question. That's what we've done it for, so you can also be thinking, and I don't have to be doing all the talking. So how are we going to do this one? Well, I'm going to do this question, finish it, then we'll go to the competition question, and then we'll take your question. So let's move on this one. So I need to get the potential difference across the voltmeter. What don't I know? I know that V is equal to I times R, but I don't know the current here. If I knew the current through this part of the circuit, I would be fine. So that's one approach that you could go to. You could go and say, okay, so I have 2 amps coming into this part of the circuit, and one part is going to go there, one part is going to go there. Now, recognize what's the ratio, and I've said this earlier, what's the ratio of the resistance? There's 4 ohms here, and there's 16 ohms here. So, guys, I hope you can see that's a ratio in the different branches of 1 part to 4 parts. So a total of 5 parts. So what do we know? That the current is in inverse to the resistances. So it's opposite. So the current, 4 parts of the current will go through there, 4 of current, and 1 of current will go there. So that means that 1/5 of the total current will pass through this bottom segment. Now, what was the total current? We've got it over here. The total current was 2 amps. So if I want to get the value of the current, then I'm going to say I is equal to 1/5 times 2 over 1, which shouldn't be a very difficult thing to get. It's 0,4 amps. Check it out. Make sure that you've got it sorted. Make sure that you understand how we do that. That's a quick way of getting the current. We would then next go through the formula that says we want the potential difference, so it's 0,4 times the resistance, which is 8. 0,4 times 8, I get it to be 3,2 volts. Let's check that this is the right answer. And I'm going to check it by doing a different method. If I'm not familiar with the ratios, then don't try them. If you must practice them to make sure you're familiar with them. But it is one way of doing it. The other way of doing it is to say, well, let's work out the potential difference in the other parts of the circuit. So what I'm going to do is I'm going to work out how much potential difference is used up over here in the 2 ohm. Well, V is equal to I times R. So that's going to be 2 times 2. So I recognize 4 volts is used up over there. What about in the battery itself? Well, I recognize here that V is equal to I times little r, and its I was 2 amps times 0,8, which gives me a total of 1,6. 1,6 plus 4 volts tells me the potential difference that has been used up everywhere except in the parallel section. So the V that's not in the parallel section, if I write V max, I think you'll agree, is equal to, or the EMF, let's rather write it as EMF because that's what they've given it to us, as we can say, we know that EMF is equal to the V of V1 plus little v in the battery plus V of the parallel section. So I know that that's 12 volts. I know that this part here is 4 volts. I know that in the battery it's 1,6. And all that I'm left to do is to find V parallel. So if I do that, let's just get the calculator out. I know that you can do it in your head, but I'm running out of time, so I'm going to do it on the calculator. I'm going to say 12 minus 4 minus 1,6. And that gives me an answer of 6,4 volts. Now, you might say to me, but hold on, that was the parallel bit. That's right. So what do we know? We know that across here, across the 4 ohm, across the parallel section, it's 6,4 volts. But we weren't asked 6,4 volts. But we weren't asked for the reading across the whole parallel section. We were across half of the parallel section. Only this part. Can you see it was 8 ohms plus another 8 ohms? So we know that those are in series. What do? You divide by 2. So it's 6,4 divided by 2. I know that I'm not setting it out very carefully, but if you take that, we know that the parallel section was 6,4. So that means, therefore, we want half of the parallel potential difference, which is 3,2 volts, because it was 8 ohms plus 8 ohms. What do you notice? We got the same answer. This confirms the beauty of electricity, because it doesn't matter what question you're doing, there's always more than one way of answering it. Katlego, what about that competition question?
Yes, I think that we should. But before you do that, just a few minutes, if you can just answer Shikash's question. She says, hello, I want to know if there's any other way to work out internal resistance. And she really needs to know this.
Okay, remember in this question, we were given internal resistance. So guys, internal resistance was given here, but let me make sure that you've got this sorted out. And we're going to do that on the competition question.
Okay,
so
cool.
Let's go to the competition question now, and we'll sort it out there.
Awesome.
Okay, so I'm going to work through it with you. We were given all this information, which we went through at the beginning of the show. Every time I get a question, whether in physics or really in chemistry, I like to draw a diagram. With a circuit problem, particularly, draw a diagram. So let's do that. We're told that we've got a circuit and we've got a battery. That doesn't tell how many cells there are in the battery. And it tells us there's a switch in it, there's an ammeter, and we recognize there must be some sort of resistor in that circuit as well. We recognize that on open circuit, the potential difference, the voltmeter is connected in parallel, and it has a reading of 12 volts. Now, the same circuit, nothing else changes. The same identical circuit, 1, 2, 3 cells, connected to a resistor, connected to an ammeter, and the switch now is closed. The potential difference reading on the voltmeter is now different. It's 11,5 volts. Now, guys, this reading is EMF. This reading is the potential difference external to the circuit. And what you've got to recognize is here's the nub of understanding where internal resistance comes from. What you've got to recognize is that each part of the circuit uses up energy. So energy is used up in the external part of the circuit, and it's used up inside the battery. The current in the series part of the external circuit is the same as the current in the internal part of the battery if the cells are connected in series. And most of the time, for practical purposes, they will be. So what we need to recognize is that this thing, EMF, is used up in 2 ways. It's the V external plus the V internal. Now, if the potential difference, if there's no current in the external circuit, well, then you're going to find EMF is the reading on the voltmeter like we did over here. This is the EMF. But when we get to the switch being closed, then you need to recognize V external is equal to I, R external, plus I times little r. And really, that's how you're going to work out the internal resistance. What made this easy was that we gave you this value. We gave you the value of I times R, or V external. Okay? We said that's 11,5. So if I wanted to find this thing, which is V internal, sometimes called lost volts, what am I going to do? I'm going to say in my example here, lost volts, or I little r, is equal to EMF minus V external, which is equal to 12 minus 11,5, which I think you can see is 0,5 volts. Now, go back to the question, and you will see that on the question it said that the ammeter reading when the switch was closed was 1 amp. So I hope you can see now, to calculate the internal resistance, it's going to be the difference between EMF and V external divided by the total current, which in our case, it's going to be 0,5 divided by 0,5, which, oh sorry, divided by 1. Hey, that's right, it was 1, it wasn't 0,5, it was 1 divided by 1 amp, and that means that the internal resistance is 0,5 ohms. So our competition question for today, the correct answer was B. Now guys, before all of you say, yay, I've won, well, I hope you've got the answer correct. But not everybody can be a winner. We're going to we've put the names in a hat, and we'll announce the winner just before the end of the show. So please don't get it too excited. Kadleko, there were some other questions. Have we?
Yes,
we've got some.
I'm just looking at some right now. Sidonia asks, must we always calculate the series one before the parallel as in the example?
So in that question that I did previously, let me just get it up. We were looking here at this series resistance, and I'm presuming that's what she's referring to. That resistor was in series. You've got to take account of it, Sidonia. You can't ignore it. It's part of the total resistance. You don't have to do any calculation with this, just don't forget it. Make sure that when you're calculating the effective resistance, you identify which resistors are in series, which are in parallel, and don't forget to add things in. I know that sometimes we make mistakes and we do forget, but try not to in this case.
Also, John, very briefly, just linked to that, Naomi asks, how do you know they are in series, not parallel?
Okay, so if in any circuit, let's just recognize this. You're given any circuit. What you've got to do is you take your pen, and I haven't got long to do this, and you simply take your pen and you plot your pen. Where you can go without picking up your pen, that part in series, there's a join. Anything not in that part is not in series.
Okay.
So I hope that's answered the question. Unfortunately, guys, we've run out of time, but please stay tuned and make sure you pick up. We will be back to support you on Friday with some chemistry. Over to you.
Thank you, John. Thank you for such an awesome lesson. As John said, we do have a winner. And if you are this winner, then you must send through all your details, okay, so that we can send your stuff to you. Your name is Palesa Mokonyama. Palesa Mokonyama, you are our winner today. You win these 3 CDs. You win this textbook, which is a study guide and study notes of physical science. And you win the t-shirt, like the one that I'm wearing now. So make sure that right now, right away, you send through all your details, because it is very important that you get your stuff. Thank you, Mindsetters, for such an awesome lesson. You guys were absolutely amazing. Remember, there's a repeat at 4:30 today. So don't forget to catch it if you want to. Bye-bye, guys. See you next time.